Now we have to figure out what happens at the terminal button. Chemical communication between the neurons. So everything we just talked about was our electrical communication. So if you understood all of that, you've got the electrical communication part. Chemical communication between the neurons. We have 7 steps of chemical communication. It's a beautiful picture. What is it? A dendrite and a terminal button. Dendrite and terminal button. Which one's on top? Terminal button. So here's our terminal button. Here's our dendrite. And this is our synapse, our synaptic gap. What are these things?
Vesicles.
Those are the vesicles. Inside the vesicles we have neurotransmitters. Isn't it kind of cool to see the actual deal here? Pretty awesome. So here we go. Action potential. This electrical communication arrives at the terminal buttons. So according to that statement, where would you say chemical communication begins? Terminal button. You got it. Terminal button it is. Our chemical communication is going to start right at the terminal button. Chemical communication starts at the terminal button. The terminal button is where chemical communication begins. At the terminal button. It begins. Everybody get that? Hint, hint of the day. Thanks for coming to class. Okay, so this positive charge comes down, gets to our terminal button, which is going to make our vesicles move to the presynaptic membrane. Presynaptic membrane. Is it the red arrow or the green arrow? Red. So this is our presynaptic membrane. So you can see we have some vesicles that are moving towards our presynaptic membrane. Step 3. Vesicles open up and dump neurotransmitters into the synapse. So here we go. They're coming. They're hitting our presynaptic membrane. They're opening up, and out comes our neurotransmitters. Step 4, neurotransmitters. If you want to abbreviate neurotransmitters, capital N, capital T. Neurotransmitters move across the synapse to the postsynaptic membrane. Here's a picture. It's kind of a cool picture, isn't it? Showing it spewing out the neurotransmitters. Kind of fun. Here's a different view. This is going to be our lipid layer, more specifically presynaptic membrane. Presynaptic membrane. This one's going to be our this is our okay, so presynaptic, postsynaptic, synapses in between. The little black dots are, what do you think? Neurotransmitters. And then all along this lipid layer, we're going to have a bunch of receptor sites. That's going to be clue for our next step. So our neurotransmitters are going to come, they're going to plop onto the receptor of our postsynaptic membrane. When the neurotransmitter sits in that receptor site, the ion channels open and ions come flowing into our new dendrite, allowing ions to move into the next neuron. Ions and neurotransmitters, are they the same thing? No, the neurotransmitters, the red dot, or the red funny-looking structure, that is our neurotransmitter. What a neurotransmitter does, it's going to go and it's going to sit in that receptor site just like you would put a key into a lock. So in order to unlock the door, you have to put the key in there. The key has to fit the lock, otherwise it's not going to unlock the door. There are certain neurotransmitters are allowed to come and sit in certain receptors to open them. Okay? If it doesn't have the right lock or the right key, it's not going to open up the doors, so to speak. Okay, so the neurotransmitter is going to go, it's going to sit in the lock, it's going to unlock the doors are going to open, ions, which is sodium and potassium, are going to come in or go out. And then it starts over with our electrical communication. So now we're letting ions in, which is going to bring a positive charge to this neuron, which is going to hopefully have action potential occur, which is going to send, okay, on and on and on. So I promised 7 steps. These are 6. We're going to take a commercial break with postsynaptic potentials, PSPs. And then we'll go back for our grand finale of number 7. Postsynaptic potentials. Changes in the electrical charge of the postsynaptic membrane due to chemical communication. So in good old plain English, what is that saying? Okay, so down here, this is going to change charges because of what? The ions, what did we call it? Chemical communication. Because of all this stuff that just happened right here, it's going to change the charge of this dendrite right there. Okay, so basically in plain English, all it's saying is this changed charge because of all this chemical communication that occurred. So we have two different types. First, we talk about excitatory postsynaptic potential, EPSP. So with our excitatory postsynaptic potential, what it's saying is this new neuron turned to what charge? Positive. So it's gaining a more positive charge. On the flip side of that, we have inhibitory postsynaptic potential, which is the same thing, only instead of becoming positive, it's going to become more negative. Okay, so we're going to do something to demonstrate this for a second. If you take your arm, bend it at the elbow, and touch your shoulder. Okay, so everybody's doing that. If you look at the top of your upper arm, this portion of your arm is sending an excitation message. So we're having EPSPs happen up here. Down below it, we have IPSPs happening. In order for us to be able to move our arm, we have to be able to have both of these, IPSPs and EPSPs, in order for this to happen. Okay? So when your muscles are contracting, like they are up here because you're showing off your big, strong muscles, right? Because that's happening, we have excitatory postsynaptic potentials occurring. Okay? Down here, where nothing's happening, we have inhibitory. These are all going back down to a negative state. Here we go, step number 7, which I promised back from commercial break. Step 7 is summation. Summation is a term. Terms are often used on exams. The definition of this term would be adding postsynaptic potentials. So in this first picture, we're going to take 3 EPSPs, which means what? Is it positive or negative EPSP? Positive. So we have basically 3 positive charges. They're going to come together and summate. We're going to add them all together. If you take 3 positives and add them together, do you have a net positive or a net negative? 3 positives. Bring in 3 positives. Still positive. 1 positive, 2 positive, 3 positives. Still a positive. Okay? If EPSPs summate and there is an overall positiveness, it can help cause that action potential. EPSPs summate to cause an action potential at the axon hillock. When we were doing your slides, did we talk about where action potential is determined? The axon hillock. You got it. The axon hillock determines whether or not action potential is going to occur at the axon hillock. Is the determining spot to where action potential occurs in the axon hillock. Just in case you didn't write it down the first 3 times. The axon hillock is the place where action potential is determined. If we're going to have an action potential, if we're not going to have an action potential, right there, axon hillock. Which is great if you know where the axon hillock is. Where's the axon hillock? Down here? No. How about up here? No. How about right here? Yeah, right there. Okay, so this little piece right there is where the axon hillock is. And it's labeled on one of your picture slides. And you go with my pointing. Over here we have an EPSP and an IPSP. EPSP is what charge? Positive. IPSP is a negative. You add a positive with a negative and you get neutral. So EPSPs and IPSPs, they're going to come together and summate, cancel each other out, and make it less likely that action potential will occur. Okay, so remember, here we are, we're down at negative 70. We start bringing in some positive charges, bringing in some negative charges, positive charges, negative charges, positive charges. Finally, we hit this area, which is the borderline called the threshold of excitation. So this is where all of this is happening. Here's a different look. There's enough EPSPs adding together. We're down at our negative 70. We start adding in some EPSPs. There are enough EPSPs adding together. Okay, here comes some more great animation. Everybody ready? Okay, watch that little bubble down there. So far we have 1 EPSP. You see the little 1 down there? We're going to add into another one. Ooh, look at that. Is enough to hit our threshold? Nope. So let's add in another one. Not quite there yet. And boom, we hit our threshold of excitation and action potential fires. So this summation is what happens between the negative 70 and the threshold of excitation. Okay, so when we left off with our chemical communication, we still have what hanging out in our receptor sites? Neurotransmitters. So our neurotransmitters are still hanging out in our receptor sites, which means what's still happening right here? Ions are still coming in. Eventually we want that to stop, right? So our next step is reuptake. The neurotransmitter gets sucked back into the presynaptic neuron.